Test, test. All right, let's get started. Welcome, everyone. Thank you very much for coming. I know it's the last talk of Build, the best one, saving the best for last. I'm really excited, to share with you guys how you can most quickly and effectively bring all those concepts and ideas that you know in the OpenGL ES and Android and iOS world and bring that to the Windows Store. I'm Phil Naparolsky, and I'm a program manager on the Windows ecosystem team. And I'm here with Doug Erickson, who's the senior content developer for Windows, one of them. So all that documentation that you know, love, and sometimes hate, he's one of the guys to blame. And I'm also here with Richard McKinney, who's the CTO of Halfbrick. And we're hoping that you walk out of this talk with a better understanding of what it takes to port your game. The scope of that and the understanding of those high-level concepts. So let's dig in. I'm going to start things off by just giving an overview of the language options and Visual Studio. Then I'm going to pass things over to Doug, who's going to do a deep dive into the graphical side of things. And finally, we'll wrap things up with some real-world experience from Richard McKinney. So when you think about bringing your game over to the Windows Store from other platforms, Android and iOS, maybe you've been on Android and used their native development kit to develop using C++. Well, we have a great story there. If you want to use DirectX, which is the analogous thing to OpenGL ES, then C++ and DirectX is our officially supported option. But let's say you developed a game on Android purely in Java. You can absolutely use C#, which is somewhat similar to Java, through third-party libraries like SharpDX and SlimDX. And if you want to quickly put together a UI, a user interface, we have a UI toolkit called XAML, which works great with DirectX, and that's most similar to, say, AXML on Android, or to some extent, the UI kit on iOS. And you can have these completely separate. Say if you want to have XAML for your main menu, just to get things started, and then have XAML plus DirectX for your in-game options. You can use separate framework views if you want, and we have samples online that illustrate that. So I'm going to dive into a quick getting started with Visual Studio sort of demo. And what I want to show here is how you can quickly get going using the Visual Studio templates. So here I'm opening up a new project, and under the Visual C# Visual C++ Windows Store option, you'll see two templates that will most apply to you if you're coming from the OpenGL land. The bottom one is if you want to use DirectX and XAML together, say DirectX for your immersive graphics, XAML, that UI toolkit for your front-end user interface. This is the template you'll want to start with. Because we're going to focus mostly on graphics, though, I'm going to go with the pure C++ and DirectX template to start with. So let me go ahead and name this My Super Game, and go ahead and create that. And let me just run it, so you guys can get an idea of what comes stock with a template. And it's very simple. It's enough to sort of illustrate a starting point for you, though. And what you'll see when this runs, you'll see a nice spinning cube with a frames per second timer. And the key here is, in this template, we've architected it in such a way so that there's a different class for each renderer. And then there's a main class that sort of manages those renderers. And the reason why we did this is to kind of separate the rendering portions from the actual OS application presentation logic. And I'll show that a little bit more in the code. So let me go back to Visual Studio. The first file I actually want to show you is the package.apex manifest file. So if I double-click on that, open that up, and let me stop this from running real quick. What you see in this file is something that describes the package that is actually created. So it's very similar to an extent as the manifest package, the manifest file on Android, and to some extent the plist file on iOS. When you actually build and compile and build your project, you get an exe file out, and all of the assets and content that you've included in your Visual Studio project is going to be combined with that exe package into what's called an AppX package, which is essentially a .zip file. You could actually open it with a .zip reader, but it's an AppX package is what we call it. So this AppX manifest file sort of describes the capabilities and whatnot of your app. So down here you can set the logo for your live tile. Let's say you have in-game advertisements and you need to use the internet. We have a capabilities tab, so when the user actually runs your game for the first time, they'll be prompted, hey, this app wants to use the internet. Very similar to how on Android that happens today. When you first create the Visual Studio template, though, there's two files that are open. And this is the Your Game main class. And this is just a C++ class. There's nothing unique or special about it, other than that it's the manager for those two rendering classes that I mentioned earlier, one for the cube and one for the frames per second text. So you can see here there's two public methods, update and render. And what I'll get into later is there's another class that just calls this, and this will simply update and call the rendering code of those two renderers. And down here is where we have our pointers. Now, we're using a little bit C++11 in here. Just by a show of hands, how many of you are familiar with C++11? All right, about 4%, I would say. This template is actually, it's really awesome. C++11 is not going away. Now's the time to start learning that. So we've included a number of C++11-like things in the template. So you'll see unique pointer and shared pointer kind of scattered throughout. I encourage you to learn much more about that. But all you have to know is we have a pointer to each of the renderers here. And later I'll talk about the device resources class. We have a shared pointer for this. And all you have to know about shared pointer is that it's a reference counted pointer. And there's a little bit more to it than that. But device resources is a class I'll go over shortly as well. Let me now show off the app class. This is somewhat of a special class if you're doing Windows Store app development. The first thing you'll notice is we're not defining this as a class, we're defining this as a ref class. So this is something we introduced not because we're Microsoft and that's just the way we do things, but because we wanted to have this common sort of infrastructure among all the programming languages. And what that enables you to do is bring this code kind of to a higher level that C# and JavaScript could potentially tap into if you wanted to go that route. We call this the C++ component extensions, and the WinRT class that I'm creating here is one aspect of that. Down here you also see something, the circumflex accent, the caret symbol, whatever you want to call it. That is a WinRT handle, is what we call that. Just a reference counted pointer, like you know and love it, but it's on that WinRT layer that I was kind of mentioning earlier. Then we're also inheriting from this class called the iFramework view. Now, when the operating system, when Windows 8 actually goes to start your app, what's going to happen is whatever class has inherited from the iFramework view, Windows 8 is going to call 4 methods to kind of initialize things. Initialize, set window, load, and run. And then on occasion, and rarely, it'll call uninitialize. And so these are things that you will actually implement. And we have great documentation online about this. I encourage you to learn more. Also in this class, we have all our event handlers, as you can see in the protected variables. And down here, we have that unique pointer to that main manager class. So let's look at the actual rendering code just a little bit, just the file structure. In here we have our sample 3D scene renderer. Again, this is just a plain vanilla C++ class. And then we also have that sample frames per second text renderer class. We also have this shader structures.h file. That's where we're storing the actual structures that are going to be passed to your vertex and your pixel shaders. So here we have a constant buffer, which Doug will talk a little bit about later, that holds the model view and projection matrices. You don't have to do it that way. You can just pass the MVP matrix. That's fine. But then we're passing, in the C++ code, we have this structure that says we're going to pass a position and a color to our vertex shader. So over here we have our vertex shader. Instead of GLSL, it's HLSL. Really, there's only a small syntactical hurdle that you have to get used to HLSL, and I think Doug will cover that in a little bit more detail. But HLSL, it's great. I love it. It's a little more object-oriented than GLSL most times. You know, you can have structures laid out there. What's great about Visual Studio is if you right-click one of your shaders and go to Properties under HLSL Compiler, you can actually set what type of shader it is, what's the type, where's the entry point, and also the shader model. In this case, shader model for level 9.1 is the default one. Finally, let's look at the device resources class, just briefly. And I know I'm kind of breezing through this, but hopefully you can watch this later on Channel 9 and kind of get a better understanding. But the final class I want to cover is device resources. And this is hopefully a class you won't have to touch that much. It's where all the DirectX and Direct3D and some of the Direct2D initialization happens. So one method I do want to show you in device resources is where we create the Direct3D device. So Doug will talk about this more in detail in just a minute, but this method, you'll be passing, do you want to use the hardware or warp or software rasterizer? What feature levels does it support? And out of that, you'll get the feature level of the machine that you're running on and a pointer to the device, the Direct3D device, and the Direct3D context. Now, what's a feature level? Well, up here you'll notice this array where we actually set what feature levels are going to be supported by your game. So a feature level is really just a generational grouping of machines with a certain graphics hardware. So more power-efficient machines, say like the Surface RT and other ARM devices, many of the launch ones were feature levels 9.1 and 9.3. They supported a number of things, pixel shaders, vertex shaders, shader model 4, level 9.1. But going up to feature level 10, that might be, you know, most notebooks today, support things like instancing. And your high-end desktop machine, that's most likely feature level 11, where you play all your AAA immersive games. So that kind of gives you an overview of the new templates that come with Visual Studio. The only difference between the one I showed and the one that includes DirectX and XAML is that app class is a XAML page instead. And really, XAML under the hood is using an iframework view. But now I want to pass it over to Doug Erickson, who's going to do a deep dive into really the graphics side of things.
All right, let's see, yeah. Okay, I'm Doug Erickson. I'm just going to quickly run you through the general overview of the concepts you'll need to understand when porting from OpenGL 2.0 to DirectX 11. And there's going to be a lot of information thrown out here pretty quick. If you want me to slow down, just yell, "Slow down, bro," and I will try to decelerate it a little bit. But we are going to go pretty quick through this, and as Phil noted, you might want to take some time to look at this in Channel 9, and we've got some links to documentation that expands on this in a lot more detail. So, and at the end, I'm also going to do a very simple porting demo, porting a very exciting Phong shaded sphere. I hope you're all familiar with Phong lighting because it's pretty simple, from OpenGL using the Kronos Group's sample implementation to DirectX 11. So we'll walk some of these concepts Phil was talking about and see actual code mapping between what you're used to seeing in OpenGL ES 2.0 and DirectX 11. If you're coming from 1.1, I'm sorry, it's going to be a real challenge for you, moving from a fixed function pipeline to a unified shader model. I'll try to make callouts every now and then if that'll help. And if you're coming from OpenGL 3.0, awesome. There's so much similarity, and you're setting yourself up well to work with the DirectX 11 feature set. So onward. OpenGL 2.0 and Direct3D, they're both designed to do the same thing in a very similar way, and that is render graphics using a pipeline with shader resources attached to it. You're going to pass it in vertex data, and along with some graphic resources ranging from buffers to textures to stencils to what have you, you're going to transform, alter, and enhance that data, specifically through the use of those shader objects. That said, OpenGL and DirectX have slightly different ways of regarding that pipeline, and there's really two that I want to focus on. I mean, there's a lot of nuances as well, but the specific ones is that OpenGL, as you well know, is vendor-specific. Platform vendors have their own implementations, Apple, Google, as well as, say, NVIDIA, AMD. Microsoft's is what we call vendor agnostic, meaning we have one set of APIs that covers all vendors. Vendors have to adhere to the DirectX specification and platform when they create their drivers, and we provide actually a couple layers of abstraction above and beyond. Whereas with EGL, most of it's fairly opaque. With DXGI, we'll give you access to that, and we'll take a look at that in an upcoming slide. Also, OpenGL ES 2.0 is largely a set of flat APIs. DirectX provides you with interfaces, virtualized representations of the device and the device context, and has the methods defined on them. And when we walk the code, you'll see some examples of that. So we'll see how this all kind of plays out in the next slides here. What do I have to worry about? So this is just sort of a set of caveats, just things to keep in mind when you're porting. First of all, DXGI, the DirectX graphics interface, is a graphics sublayer that exists below Direct3D, provides you access to a lot of the functions that EGL provides you for DirectX, only much more explicit, much more explicated, allowing you access to a lot more hardware options, like things like what we'll say in DirectX terms, swap chains for multi-plane rendering, which means a different way of representing the back buffer and different tricks you can perform with hardware resources. DirectX, as we noted earlier, also has that device abstraction, ID3D 11 device, which is one of the primary interfaces of two, which we'll talk about in the upcoming slide as well. Again, you'll see abstractions of a lot of GPU properties and behaviors represented as interfaces. They're COM interfaces. Don't panic. If you're developing Windows Store App, you won't need to learn COM. Just use the magic COM pointer, as Phil showed, and that will handle all the reference counting and all the nasty things that COM used to distress people about for you. And just one sort of a general concept to keep in mind, since the graphics devices represents an abstract interface, think of the GPU as something from which you acquire specific resources. I'll be using that metaphor a lot in the slides to come. Also, here's the biggest thing in porting, right? And it's kind of the elephant in the room, is that ultimately, this is about learning how to use Windows and program against Windows. And I'm not going to go into that in detail, but you can simplify this dramatically if when you've created your game code base, you've done basic things like separate the rendering logic from the game logic. The more you've separated it, the easier your port is going to be. Our templates are structured in Visual Studio 2013. We've created a new set of DirectX templates. If you've used the ones in Visual Studio 2012, they're a little bit cumbersome. These ones more accurately represent, I believe, the way game development happens and really separates your game loop away from your renderer and allows you to keep those concerns separated when working with them. So you can focus on porting your rendering logic and worry about all the understanding the Windows Runtime API to move to DirectX. Lastly, again, we focus a lot on asynchronous programming in that. That's probably, most of you are probably comfortable with that, but if you're not, take a look at the parallel patterns library, the ppl task.h, and understand the basic Lambda syntax. I'll show some quick, simple examples of that in the demo. Or if you're feeling frisky, go ahead and use iasync operation directly. All the tasks do is wrap that. And then we'll talk a little about porting GLSL to HLSL. It's easy. It's fun. You can do most of it with a macro. Very quickly, this slide looks, you don't even need to read the text, because I really just want to point out, you're doing the same dang thing between OpenGL 2.0 and DirectX 11. You're acquiring some sort of window, right? You're acquiring some sort of 2D resource that you'll use to provide to that window that you'll draw into. You'll create and attach resources, or you'll create a drawing context. Then you'll create shader resources that you attach to it and buffers that you provide to those shader resources. And then you draw to that 2D region, what we'll call a render target in DirectX, and provide that to the back buffer and flip it. Just wanted to reassure you all conceptually, there's not that much magic going on. EGL to DXGI, I'm going to keep this one fairly short. Suffice to say, the most important thing to understand is the idea of a core window. It just wraps an HWind and provides your event dispatch infrastructure. So when you're handling events, you'll do it off the core window using the events that Phil showed you in the template and the core dispatch type. Also, you'll use the D3D11 create device to create device and a device context. That device context is very similar to EGL context. The device, again, there's no real analog for. That's just the way, again, that's how we are vendor agnostic to some degree. And then you'll acquire that D3 device and to create a swap chain. A swap chain contains is where you'll provide the back buffer. That's what's to use to actually perform the, when you do the flip to display to the, to send the render target to the display. And that's the magic. So porting to a Direct3D 11 framework, there's two critical interfaces that I mentioned earlier. These are going to be the backbone of your destination rendering code. The D3D device, in this case, ID3D 11 device 2 is the latest version of that API. And this is very similar to your, it has on it the functions that are similar to the ones you use to create specific resources, like your shaders, your buffers, your GL create shader, your GL buffer data, your GL gen buffers, where you acquire texture resources, that sort of thing. One thing I'm going to mention here, and I'll mention also a little later, is there's no concept of a shader program. DirectX, when you create and compile your DirectX project, you also compile your HLSL files down to CSO files, shader objects that you will load in your code. So there's no, well, we've introduced with 8.1 runtime compilation of shaders, but I'm not going to talk about that. In this case, your shaders will be compiled, and you'll simply load them using device APIs. There's no master shader program that will perform the runtime compilation of shaders for you. The device context is where you'll actually do all your rendering. It's where you'll set up your it's where you'll start passing in your vertices and your index buffer, where you'll attach your shaders and attach your resources and perform all the rendering commands, and then output that to a back buffer and display it. And you can see there's some of the similar APIs there. I've talked a lot about the notion of resources. So in DirectX 11 country, if you go into our docs, you're going to see we talk an awful lot about resources. Resources, when we talk about it in Microsoft language, is they're the objects used by the GPU. And they include everything from the constant buffers to texture buffers to depth stencils to sampler states. And in order to access these resources, you need views. And views are the you'll also send them to the shader stages, and they're the way for the GPU to interpret those resources. So a quick mapping then to get started, really mapping OpenGL ES concepts to Direct3D. What you call a uniform, we call a constant buffer, and we have slides on all these. What you call an attribute is actually a specific buffer that's used for vertices or indices, specified with an input layout. A buffer object is just one of something derived from ID311 resource. And a back buffer is a 2D image that that we use as a render target, and then we send to the swap chain as the back buffer. So uniforms to constant buffers. These slides, I'm not going to really talk to the code specifically. I'm just going to sort of describe them in general terms to keep the pace up. Again, I encourage you to review the code and review these slides later if you want to get the specific details out. So in DirectX, any uniform constant data is represented as a constant buffer. Typically, you consolidate all your uniform data based on what you do. Like you consolidate all your matrices into one constant buffer. We don't tend to provide them as scalar objects, so tend to if you've made all your uniforms independent, you haven't encapsulated them in some sort of struct and provided them some sort of buffer, logically group them into structs when you're creating them. Also, you're going to this constant buffer will also need an analog in the HLSL file, so that it can understand, so that the shader can understand the layout. Let's take a look at the code for that real quick. In our C code, which is in the shader structures.h file that Phil pointed out earlier, we've defined our three matrices: model view projection, and the one used for the normals. And then on the other side in HLSL, we've declared it as a C buffer. That C buffer you can kind of think of as the uniform keyword, right? The register bit, which I'll talk a bit about later, the B0, don't panic, that's just like a loc. That's like a location, right? B0, that 0 is the slot on the GPU where it knows how to access that resource. And we'll get, when we look at GLSL versus HL, we'll look at the terminology. How am I doing on time? Attributes to vertex buffers with input layout. The analog to this attribute is what we call the input layout. We'll take a look at that in code, and that one is best shown in code. I think it'll click more when you see it actually in code. And that is what tells the GPU shaders how to interpret the struct you use to represent the vertex data. Things like the offset, where you would normally provide an attribute name There is what we call an HLSL semantic. It's just a little string we append on the end. And hey, let's even call it up so we can take a look at that. So let's say we have a vertex with a position, a normal, and a set of pair of texture coordinates. When we pass into HLSL, what would be the attribute position, normal, UV? To see that bit in capitals on the end, those are arbitrary strings. We call them HLSL semantics. And they are, when we pass those into the input layout, we'll specify literally in our input layout description, we'll say this HLSL semantic, this size of data, this is where it's offset from the others. So you would lay those just like you would lay out your attributes, but we're using a structure to represent them. So in OpenGL, there's really two ways that you could be coming from. One is you could be using GL enable attribute array and using the built-in vertex buffer functions, whereby you pass in the set of positions as one array, you pass in the vertices as another, or you could be using gen buffers, bind buffers, that setup where you actually do define a struct and tell a stride and offset for that. If you're doing the latter, it's much easier to point to this. But in our environment, you should, for each vertex, consolidate all the data that you want as input to your vertex shader into your vertex struct. If you're importing from a mesh or something else, make sure you lay out the structure similar to the data you anticipate loading from the mesh, and that you have all your stride and offset set correctly. Going onward. Textures. This one is one I would love to spend more time on because there's just so much we could talk about here. Unfortunately, I would need a whole hour really to go over texture, so I'm just going to apologize for that. We're hoping to have some great documentation online for that soonish, definitely before RTM. The first thing, though, the most important thing, the thing that will probably cause you the most irritation, and there's nothing I can do about it, is we don't use ETC or PVRTC texture compression formats. You're going to need to use your original assets and recompress them as DDS textures using the BC texture compression format. Now, Phil was talking about feature levels earlier. If you are supporting 9.1 to 9.3 devices, I assume you are because OpenGL ES 2.0, the range of devices it typically supports are analogous to 9.1 through 9.3 feature sets. You'll need to compress those textures as BC1, BC2, BC3. And I won't go into the details of those, but pick one of those that best corresponds to how you want your assets to look. Maybe check them out. If you're going to DirectX 10 level, feature level, for some reason, BC4, BC5. If you're going to support a DirectX 11 rendering path, you'll also need to provide textures in the BC6H or BC7 formats, which are optimized for that, which you'll get the best performance out of for a DirectX 11 feature path. So yeah, that's a lot to consider, and there's an investment there. The other thing I want to talk about is, well, there's not really a direct analog per se in OpenGL ES, is the idea of sampler states. When you're defining your texture, so you're going to have different texture types, right? You might have the base texture, then you might have light maps or dirt maps, you may have normal maps you're generating separately for that, height maps. You'll want to create sampler states for the groups of those textures, and when you provide your texture to, say, your fragment/pixel shader, you also want to provide a sampler state for that corresponding texture type. So that's just something to think about. And there's a lot of text there. Again, I encourage you reading that slide. You also need to provide a resource view. So the GPU, the shader, knows how to interpret that texture. That's a little different as well. We've got pretty thorough documentation on this. And again, this will be provided online for you to use as a reference. So shaders. Conceptually, they're similar. They're shader objects, right? Our driver manufacturer would be pretty unhappy if we made them radically different. The big difference is what I mentioned earlier. Visual Studio, or you can do it through the command line using the FX tool. You compile your HLSL files as CSO files, and you'll include those as assets. And those CSO files are what are loaded as at runtime, already compiled. You don't load HLSL and compile it, or GL. You wouldn't be like grabbing GLSL from a text file at runtime and compiling it. There's no need for a parent shader program, which we already touched on, so I'm not going to go into that. And there's a lot of actually shader stages. If you take a look at the image of our DirectX 11 pipeline, which I don't have here, unfortunately, but DirectX 11 defines a lot of shader stages. I'm going to focus on the ones that matter to you the most. You see the prefix IA on some methods on the device context. That stands for input assembly. That is where you're putting together your mesh data, your vertex data. You're getting it prepared into a format and getting it ready to stream into the pipeline. Vertex shaders via set shader sets the shader, the CSO you've loaded on the pipeline, that specific shader at that specific moment in the rendering loop. The constant buffers, those are the constant buffers that you want to provide to the vertex shader. Pixel shader, same thing, only I also included PS set shader resources in there because you're probably going to be doing some texturing. And that's how you're going to be providing the resources for the views as well as the textures. So make sure you specify the register slot when you set those resources. We'll talk a little bit more about that too. GLSL to HLSL. This is probably the easiest part of it, but with one caveat I want to address at the end. The first thing I want to talk about, though, you all know what GL intrinsics are. They make life a lot easier if you're coming from 1.1, well, fixed function. They're sort of like the, inside the shader, they're sort of like fixed function behaviors. There are ways of assisting you. GL position is probably one you care about tremendously. The corresponding HLSL system value semantic. Now, I mentioned semantics, so I want to be clear on this because I don't think our documentation is precisely clear on this sometimes. HLSL semantics typically are arbitrary strings that you use on the CPU versus the GPU, that's so they know how to correspond the data between the two. SV semantics are reserved terms used by the system that we specify on input between stages, and you can think of them as your varying data. When you mark that, that is data that you want interpolated, rasterized, or something for the GPU to do on it when it exits one stage and enters the next, usually interpolation of some sort. That is what SV position does when you specify an element in your in the output for your HLSL vertex shader. Your position data, you would mark it as GL position, and it will rasterize that to a pixel coordinate in your render target. And again, registers, there's 3 registers types. Those are your locations. You can think of the slots where it expects to find that particular data element. You specify them as, for buffers, constant buffers, you would specify using B and then 0 through, depending on your feature level, some number. For textures, it's T. And for the samplers used to access textures of that family, of that type, whatever logical grouping you have for it, you'd S. Now, one point I want to bring up is in the process of porting GLSL to HLSL, especially if you do use tools for that, doing macros or just doing some sort of programmatic mapping, run shader analysis tools at the end. I'm not trying to be, I hope I'm not being patronizing with that, but you'd be surprised at the difference in instructions when you take a look, say, with AMD Shader Analyzer, the GLSL version, and the HLSL version. They are different compilers, and it's just a good idea to check them out for performance reasons. So I really recommend that. And there's some, when we post this on Channel 9, there's some links. So now, oh good, I've got enough time. I want to go through a demo. While I'm setting this up, does anyone have any quick questions I could address? Absolutely. Yeah. Yeah, I'm aware that's a ton of information to throw at you. This is one of those things that really is best given with documentation. I hope just everyone kind of understands the general thrust that, first of all, the same concepts really do apply. There's just a lot of mapping of language from the Kronos Group's world to our world, and then just some design pattern differences and some different code API differences. Oh, I'm sorry. Yeah, there we go. And we love your feedback. Please send us. There's a feedback link on the documentation. Send us our way. I actually do read it. Sometimes I cry, sometimes I cheer, but emotions are awesome. So we're going to take a quick look at this, and this is some seriously exciting stuff, folks. And I am on number 6. I was warned not to touch anything that was not normal because I have a habit of destroying things. So, and let's hope my tendency to break things does not apply to this demo. All right, here we go. So I just credit where credit is due. I used the Kronos Group's reference implementation of this for Windows. So if I'm sure all of you are writing Windows OpenGL ES apps, right? No. You're probably coming from Java, C++, or Objective-C. Bear with me. I had to use a Windows implementation for this. So let's take a look at the OpenGL code. And I just want to very quickly, if you look at the structure here, this is a very simple application that does Phong lighting. Originally, I was more ambitious and had a BRDF, and I realized nobody wants to look at my lousy math. So let's look at I decided to go with Phong instead. So we've created here in the header file a very simple render object with all the things you'd expect to see on it. Vertex buffer, normal buffer. The locations of them, all the data I need defined as uniforms to do Phong shading. So if you had a recent CS graphics class, you're probably kind of twitching a bit. I like the way OpenGL does matrices. I don't like multiplying them on the GPU, so I'm going to be porting that analogously over to my other example. And the most important thing, though, that I want to point out here is these three functions. Because you may have noticed when Phil was doing his demo, you saw at least update and render, right? There's also one here that I've created called init, which most people have an initialization function that we use to set up the resources before we start the rendering loop. We have an analogous function, actually, that's already provided for you in the template that is create the oddly named create device-dependent resources. That name is meaningful to us as people who develop DirectX templates, but that's really what you'd commonly use to initialize your per-scene resources as well. When the window gets changed for some reason for the Windows runtime, someone closes it, gets rid of it, someone changes a graphics adapter by hitting their whatever key to change Optimus over. That was where we'll recreate the resource. That's also a great opportunity to obviously recreate all your per-scene resources. So I'll be emphasizing that quite a bit when I move over to the other template. And just a real quick cursory scan through the code here, just prove that there's no one behind the scenes. In fact, I'm going to extra prove to you that there's no one behind the curtain because I made a slight misconfiguration in my project file earlier. Here's the init function, which does all the default values that I want to do to make a green sphere spin around the y-axis, Phong shaded. I'll take this a little slower, see if you want to read the... I've made some cute comments in case I forgot to note them. Set our attributes. Set our uniform locations on the renderer. Again, note if you want, there seems to be people of two minds of how they want to handle attribute arrays in or vertex buffers in OpenGL, and I want to make everybody happy, but so I did also have that code path in there as well. And then update function, which does recomputes the matrices. Thank you, Kronos Group, for providing me with functions. I actually had to add matrix inverse transpose. Not the most fun function in the world to write. And then rendering. Again, this is all you're used to without probably the Java class syntax on it or the Objective-C representation. But same methods, or same functions, I should say. And let's just build that. And let's clean it and build it, because I feel like feeling legit. And because I screwed up my project, I actually have this right to a separate directory. But let's just see, I'm not cheating. There's a timestamp right there. And there's a VRDF version as well. Look at that. Look at that. Oh my gosh. I would get probably a B plus, maybe an A minus in CS241. All right. So let's put that aside for a second. And now we're going to take a look at the DirectX version of this. And I'm going to draw direct analogs to what I did in this, because I tried to port this as reasonably authentically and as close as possible. Let's stop running that. I was actually confirming that I wouldn't. Oh, good. It's dead. OK. So Phil pointed out to you. I put my stuff on the left-hand side. That makes me cool. Phil pointed out to you, I've renamed simple 3D scene renderer as sphere scene renderer. That's all I've done. I've used the identical templates to what Phil showed you. I've made very few modifications to the templates, none in any of the things that matter, like the device rendering, like the device resources or the main app. I tried my best to completely unpollute the template with my own code and focused entirely on changing one file, and that was the simple 3D scene renderer, and I believe I succeeded. So again, no one behind the curtain. If we take a look then at the header file for this, right here, these are the functions that are analogous to what was in my GL app. Init, which we called create device dependent resources, update, and render. The only difference with update is I kept the step timer in there because I love the frames per second code. It makes me feel warm, fuzzy to know that I can make a sphere rotate at 60 frames a second. No one's hiring. These are the only functions I added. Basically, I tried to straight port as much of the EGL code as possible. Or sorry, the Kronos Group's ESUtil code as possible. Again, thank you, Kronos Group. You contributed to my demo. one of the ones that we're going to talk quite a bit about is the input layout, because again, this is your attributes. These are where your attributes are going to define what you're going to focus on when you're porting your attributes. We also define our vertex shaders and pixel shaders using the corresponding these vertex buffer and index buffer, which are again derived from the buffer or the shaders, their resources. Here's all our buffers that are defined. This little m underscore bit, that's just Microsoft's internal way of specifying global variables for a class. And then we've got our shader resources, or shader structures. And if we look at shader structures.h, let's take a look at our definitions of them. So what we had previously is two uniforms. In the prior sample, we had a uniform for position and a uniform for normal. We have here as two fields on a basic vertex struct. I've consolidated them into one structure that's also going to be provided as a constant buffer. So you may notice here this XM float thing. I use DirectX Math whenever possible. There's a really, really good reason for that, as it guarantees the 16-byte alignment that makes DirectX happy. Otherwise, you'll get lots of interesting errors. The good news is when you get those errors and you immediately put them into a Bing, you will get tons and tons of people telling you exactly how you screwed that up. And there's two ways to fix that. You can declare underbar, declspec, align 16 on those types and get into some Win32-esque programming. Or you can just use DirectX Math types, which are basically wrappers for auto-align types. So I recommend you do that. Also, they just provide nice analogs to what you're going to be using in HLSL as well. And here's, look at that, MV matrix, MVP matrix, Microsoft, and then our normal matrix. The light position I just put in a single constant buffer because I felt like it. It also maps what I did into OpenGL. And then all our material data wrapped up in one constant buffer type as well. So let's take a look at the CPP code. Again, you'll notice there's not a whole lot of, well, there's some pointer passing, but if you've dabbled in XNA, it's really not a huge leap into DirectX anymore. Although the APIs now have much longer names and are defined with COM syntax, sort of, we've still wrapped a lot of functions, and we've brought over a lot of things from XNA, like DirectX Math, Xaudio, Xinput. So it's again, if you've dabbled in that a bit, I think you'll find a lot of things familiar here as well. So look at that. We are loading our compiled shaders. They are compiled by the FXC compiler at runtime. You'll just load them. Note that we are reading data asynchronously here, and I wish I could spend this is so we create these as asynchronous tasks using Lambda syntax. It's a bit character heavy. I recommend you read up. We have some awesome guidance. A coworker and friend of mine wrote on PPL guidance on using the PPL and on the task type. Check that out. It really, once you get used to it, it's fun. It's a lot of fun. I think it's fun. So we create our vertex shader with that CSO. We acquire the direct 3D device. Get 3D device is a wrapper. That's part of our template that just acquires the device for you off the device resources. Here's the bit I want to talk about. This is your input layout. Position and normal you can think of as your attribute names. So you will use this description struct here, D3D11 input element struct, and you will provide a position name and a normal, and those will correspond to that, and those will correspond to the attribute names that you're used to providing. I've got not too long, so I'm going to slightly accelerate here. Again, we have a lot of similar samples online to this that you can use to review this. Then we also call create buffer to create our constant buffers. Very similar to setting locations for uniform data. And this is all in our init loop. Then we do the same thing for the pixel shader. We create a task to load the pixel shader and create its constant buffers. And here, since the light uniform is static, I create that init time rather than updating in the update loop, because why? And here, the same with the material uniforms. So now in the update loop, or in the update function, which will be called from our update loop, I do all the calculation for the matrices such that rotation can occur. The one I really wanted to point out is, so OpenGL defaults to right-handed coordinate system. DirectX is ambidextrous if you use the DirectX math library. You can create perspective matrices and any other matrices from a right-hand or left-hand coordinate system. If you don't do that, I think it assumes left-handed, and then things can get a little hairy when you're porting meshes. So I just want to show that as an example of being able to use it in an ambidextrous capacity. And there's a lot there. This is all just funky stuff to get the matrices in the format I want them. And lastly, the render loop. I want to step through this. We create a render target view. That's going to be that's what's going to be drawn into our, that's how we're going to draw it into our back buffer. Now we're going to access that. And we set the render target. We're going to prepare a constant buffer for the transformation matrices. There's what I talked about earlier on the shader thing, the IA set vertex buffers. That's where we'll provide the buffer. And the corresponding index buffer for it, since we recommend you use triangle lists. I set primitive topology, which I didn't mention. If you do use strips or fans when porting and you don't use an index buffer, well, you wouldn't create an index buffer and you use set primitive topology to a strip or a fan, respectively. Set our input layout, very important, so it knows where to get that data. And we attach our shaders, set our constant buffers. Then we draw the objects with draw indexed, and then in the update code off the main app, we'll actually flip the swap chain. So I want to give Richard some time here, so I'm going to go very quickly through the HLSL and GLSL, and I'm just going to have a few talking points about that. Vertex shader, let's take a quick. I put the corresponding GLSL up here for reference, but since I'm not going to have a whole lot of time to go through that, I won't. Suffice to say, the important thing to take away here is where we saw the uniforms up here. Here is the corresponding context buffer. And because I love OpenGL so much, here is the varying data. I actually named the position GL position, so when I refer to it in my fragment shader, I can use GL position instead of what arbitrary name I gave it. Note that GL position I mapped to SV position, that HLSL semantic that is going to be rasterized to a specific pixel value. One really important thing about HLSL that I wanted to get to, sorry, Richard, I'll try to accelerate myself, is this is the output type. That is what's passed between the shader stages. I even called it varying pixel shader data, so you understand that this is the data that's going to be interpolated. So everything that's blocked will be interpolated when it's passed to the pixel shader. And if we go to the pixel shader, that will also be our input type. It will look like that. So there's the definition of the data in GLSL. There's the material data passed in as a constant buffer. That's in register slot 2, because I used 2 slots for the other 2 constant buffers on the vertex shader. There's the data here is the same as what we saw in the vertex shader. And SV target is the same as GL frag color, or GL frag data if you're like writing a height map or normal map, something out with a prior shader stage. And again, the code is largely the same, so let's just build and run that, and then I will turn this over to Richard. And look at that. Same thing. If we do this side by side, if we do this side by side, oh, come on. I think I just did myself a, you know what? I'm going to stop while I'm ahead. But suffice to say, I wanted to show them side by side, but I want to turn this over to Richard, who has the things to talk about in the real world of porting. So, Richard, I'm turning this over to you. Let them know how it is.
Thanks, Doug. So hi, everybody. Hi, everybody. I'm Richard McKinney. I'm with Half Brick Studios, and you may know us for such games as Fruit Ninja, Jetpack Joyride, Fish Out of Water, a lot of titles that have been really successful over the years on iOS, Android, but we've also got support for a lot of other platforms. And just last year, we brought both Fruit Ninja and Jetpack Joyride to the Windows 8 platform. They're now also available for Windows Phone 8. So I'm pretty much here to give you guys the from the trenches experience. You know, Phil did a great job of introducing how you might get started on the platform, and Doug did a great job of explaining how you might port what you have. I want to give you guys some information on the things that we ran into, the issues that caught us in certification, the little snags that we hit along the way that caused us big performance issues. So I'm definitely going to run out of time, and I'm going to have to move through, basically skip over the less important points. So definitely check out the slides online, because it's pretty summarized for you, and you can just take a look. I'm just going to go through 3 basic areas. I'm going to talk about the Windows Store ecosystem a bit, and then I'm just going to jump into both high and low level tips and tricks and performance optimization things that you can get easy wins back with. So just jumping right into ecosystem, the biggest thing you have to understand is that when you look at like iOS, there's not that many devices out there. It's really easy to know what you're working with. You can just look at the device identifiers and you know the performance. Android, you have a ton of devices and a ton of marketplaces, so it's a lot more analogous to that in terms of device ecosystem, because there's a million devices out there that can run Windows 8. Anything that could run Windows 7 can run Windows 8. So you can take those old netbooks that are 1 gigahertz, 1 gig of RAM, and you can put Windows 8 on them, and you can run anything that's on the Windows Store as long as it meets min spec. So there's a lot of devices out there. In terms of devices, it's a lot closer to Android, but there's only one marketplace, and the driver models and everything are a lot more consolidated. So if it works on one device and if it works on your min-spec device, it's much, much, much more likely that it's going to work across the board. So in that respect, you pretty much need just a couple of devices in terms of testing. What I would suggest is you start with the worst netbook you can find, just a 1 gigahertz, 1 gig of RAM netbook, and then move up to a Windows RT tablet, and then maybe an x86 tablet, even a Surface x86 tablet that you guys all got at the conference, and a beefy desktop PC that I'd use for your actual development day to day. What's that? Yeah, you could. Yeah, I mean, anything that'll give you a good range. But yeah, you want to have the low spec and the high spec, and you want to work with both. You want to be able to target those. You want to optimize the experience for a large range of devices. So you want to have those available. Now, because you want to cover the broadest spectrum of devices that you can, I'd suggest highly that you have some profiling code that you have at startup. We originally just did it's going to work approach, and we found really, really low spec devices that ran Windows 8 just fine. So we still wanted our games to run on that. So I'd really suggest that you run some profiling code on startup. For us, it's mostly fill rate. We do a lot of 2D games that are really intensive, that push just tons and tons of quads on screen, that are have a lot of alpha on them, and we do lots of different layers. So fill rate was our biggest limiter. So what we did was we just pushed a whole bunch of quads on startup, and so every time we start up, we push as many quads as we can, and as soon as that pushes us below 60 frames per second, we have an actual value that we can use to scale back, a numerical value that we can use to scale the performance around. So we can increase or decrease the size of the frame buffers based on that, and we can turn on or off effects, show less particles, that kind of thing, based on what we do on startup. And that's helped us a lot to getting everything working across the board. And so when, I guess jumping straight into the Windows Store stuff, they've actually added support for consumables. Most of your games, I assume, if you're coming from iOS and Android, have in-app purchases. You're going to have free games with in-app purchases, the standard way to go. There were no consumables when we did this, so and if you want to get your game out in the next couple of months, you definitely still need to support this old model. You do have the option of doing 24-hour expiring durable purchases, and you need to keep that in mind and consider it whenever you're doing your in-app purchase system. Consumables are only available in 11.1, so if you're just targeting 11.1, great, you have nothing to worry about. But there's some kludges that you might need to get in there for if you want to support just straight 8. So yeah, I'm really just going to give a grab bag of things at this point, and I'm just really going to jump around. I've only got a couple of minutes, so I'm just going to give really cursory overview of this information. Definitely take a look at the slides later. So the store certification process is really intense. It's a lot more intense than most of the other stores that are available for iOS and Android. So you definitely want to make sure that you're checking things early and often. The WAC tool, the Windows Application Certification Kit, is really powerful, and it'll tell you all sorts of things that you're doing wrong. So pay attention to it. Make sure you fix up everything that it says that you're doing. If that's restricted API calls, if that's, if your game's not starting up fast enough, it's the very first step of certification. They will run it. If it fails, your game will immediately come back to you. So just make sure that before you hit that button and you push your game through, that you've run it on a WAC tool and you've done it on the lowest spec device you have, because it does not scale properly. You might pass every time on a high spec device, and you might fail every single time on a low spec device. Definitely create your game in the dashboard as early as you can. Once you know that you're making your game, make it in the dashboard and have a look through all the different pages on there. Especially the description page has all sorts of fields, and if you're going to support a whole bunch of languages, everything that your manifest declares that you support, you're going to have to fill out the description page in every field on it for every single language that you have, and that includes localizing screenshots. We failed cert because we didn't localize screenshots. We failed cert because we didn't have a privacy policy on the last page once. We failed cert a million times. Yeah, just create it early on. See all those questions that you're going to have to answer on down the road. Cryptography questions. What is your classification? And yeah, just make sure that you know early and get your producers or you guys or whoever to be able to answer those questions. On WinPhone 8, just really quick, make sure that you look at the differences between Windows Phone 8 and Windows 8 before you get started. We did it Windows 8 and then Windows Phone 8. And then we figured out when we went to port to Windows Phone 8 that we made all the wrong choices in terms of the overlapping APIs. Some of them are specific. Some of them only work on Windows Phone. The ones that only work on Windows Phone will also work on Windows 8, though. So definitely check the documentation early. And if there is one that works on both, choose that one. We had to rewrite a bunch of stuff whenever we went to do the Windows Phone 8 because we were not careful about that. And then the only thing, people ask me all the time, what is the #1 platform feature for that, if sharing or, all the different things that are specific to Windows 8. Out of those, what is the #1 thing in terms of impact? And for us, it's been live tiles. For user retention, we did a lot of cool stuff with live tiles. We've got, render and texture inside of the game. So this is just an example of some of the different things that we render out. We use render to texture, save it to the app data, and then we use in the tile notification, we point to these files, and then it just cycles through. So it's pretty cool stuff. These I'm going to have to jump through really fast. So biggest point, make sure that your shaders are built for shader model 4 level 9.1. It's as low as you go, but you will find devices that are running 9.1. If you don't supply shaders for that, well, your game's just not going to render. When we did our release preview build, we found like 2 days before that our game just didn't run, like it didn't render anything. And we figured out that was why. Some of the other things I'm just going to skip over. Definitely check the slides later. One of the things, because everything is so highly multi-threaded, you're going to ask the question at some point in time, I have to do this on my UI thread. Like, you're going to come up with something that has to be done on the UI thread. It took us a while to figure out how you do that, but as soon as your game starts up, you can save off the thread dispatcher on that thread, and then from other threads, you can call into that where that stored off UI thread dispatcher is, and just call run async on it, and then whatever's in that lambda, you can run on the main thread. Performance tips, just some simple stuff here. Don't query for orientation. It's an expensive operation. We did it several times and didn't realize how expensive it was. Thought it'd be cached. Prefer BGRA over RGBA. And after that, basically make sure that you have an animated splash screen for startup, because you only get, I think it's 3 seconds before your app will get ejected it'll fail from the Windows Application Certification Kit for not starting up fast enough. So make sure that you do nothing in your initialization except start up your background threads that do all the initialization, and start some animation on the screen. Make sure that something's going on. And yeah, some devices are extremely fill rate limited. Like I said, there's some things in 11.2 that let you do that automatic scaling. I think it's the overlapping swap chains. But yeah, we had to do it manually. So scaling back your frame buffers is the easiest way to gain back that fill rate. And just test on multiple GPUs as early as you can. The different 11.1 and 11.2 features were implemented a little bit differently across the different vendors. And we saw, using one method versus using another, anywhere from like a 60 frames per second perfectly running app to we just dropped down to 1 frame per second and we were gone. So we had to make those changes real fast because we always find those right before submission. Yep, and then this is actually the biggest performance tip in terms of gaining back CPU cycles whenever people touch the screen. Add this code on startup. This one line took us several days to find, but every time you touch the screen, it gives you a pointer visualization. It's a huge CPU spike, and when you have multi-touch, especially when you got 8 fingers going across the screen, it's a huge, huge performance decrease. So just make sure you add this. It'll gain you so much performance back. Yeah, definitely just you go check out the slides to read through that again. I had to skip over a little bit. But here's some samples. Definitely go out there, check out the XAML DirectX 3D shooting game sample. I think that's one of the best ones because it covers all the different things that you might need. So yeah, I'll just hand it back to Phil to close us out. And thank you, guys.
Thank you, Richard. All right, so yeah, I hope you guys enjoyed the talk. Definitely give us feedback and give Visual Studio feedback. This is what this slide is about. I think they'll be there for another hour or so. And here are some other related talks. We're at the end of the conference, but you can find all of these online on channel9.msdn.com. And yeah, give us feedback. If you want to learn, if you want more documentation and more talks on porting from OpenGL, yeah, I'm not sure what happened to the QR code, but give us feedback in person, too. All right, thanks. And we don't really have time for questions, but I'll be around for a bit, so thank you, guys.